this area, we are using membranes which are totally different from the one that we have been discussing until now. And you will learn also how to prepare this kind of membranes. These are membranes charged, membranes in which the selectivity is not related just to solvents or to the molecules, sodium chloride, potassium chloride, but the selectivity related to the transport of ions, NH plus or potassium ions or hydrogen ions, etc. Not just molecules, but single ions. And there are important operations that can be utilized based on these membranes. Some of the most important industrial production, for example, chlorosoda production. Chlorosoda production is the basic industrial production of any industrial system in the world we have today. In any country, in Korea, in Italy, in the States, etc., when you have a big industrial complex, there will be for sure a chlorosoda plant somewhere producing soda and chlorine for the other steps. All the soda chloride production today are based on the utilization of ion exchange membrane system. All the old systems are now no more in operation, and to have an effective, not polluting production of chlorosoda, industrial plants are based on membrane system that can separate anodic and cathodic compartment and avoid any big pollution of the old system where mercury was utilized, and mercury is very poisoning compounds, or asbesto, that means filter in material that today are forbidden by law. These systems are present only in very old industrial plant. All the new ones are based on material of this kind. Much more effective, much more appropriate, and consistent with the logic of process intensification. And more than this, your battery, your accumulators, your fuel cell, and the separation process as electrodialysis are based on use of this membrane. So this is not marginal area of the membrane engineering field. We already mentioned, talking about nanofiltration, that the ion exchange membranes, they can be cationic or they can be anionic. And you know that cationic means ions charged with the charge positive, and anions are the one charged negative. And we can have material in which only cation can go across, or material in which only anions can go across. This phenomenon is related to the fact that in this material forming our membranes, the polyelectrolytes, the charged polymers that we are using for making the membranes, are characterized of having some fixed charge that are part of the structure of the polymer, so they cannot move. They can only move if you break, if you destroy the polymer. You don't want to do this. And this charge is neutralized in the system by some mobile ions having a charge opposite to the fixed one. And depending that you have some charge fixed negative or some charge fixed positive, you will have system in which we define counter ions, ions which have a charge opposite to the fixed one. And in this case, these ions are the one neutralizing the negative one. For each single negative charge, there will be one counter ion. And ions with having the same charge of the fixed one, and we call them co-ions. These co-ions will not be able to penetrate normally in this in a membranes having this kind of structure, for what we call Donnan exclusion phenomena, which is nothing more than electron neutrality law that we have to respect. The counter ion are the one that are mobile, they can penetrate in the membranes, and when one of these co-ions is going in, it means that one of the mobile ions present in the structure is going out, so the electron neutrality can be respected. The same cannot happen if co-ion is trying to penetrate, because the charge is fixed, cannot move out. So if we are just increasing, we are violating the electroneutrality principle. So this is the basic understanding of the phenomena, and exactly the previous one was a cation. Here is a case in which we have anion exchange membranes. So before the fixed groups were carboxylic, sulfonic, or similars. Now the fixed groups are just Cr2 plus or nitro group, amino group, etc. So these are just the positive one, and the counter ion will be in this case negative one, and the co-ion having the same charge will be positive one. So this one in this case will not penetrate at all. In the other case was the charge negative that was not penetrating. The counter ion, the negative one, will be able to enter in the structure to penetrate. These are ions, that means they are charged. So this is a kind of electricity that is just going across, because these ions are just a charged system, and they just the overall flux of the negative or positive ion moving across is related to the intensity, the current intensity that is crossing the system. We will define, I can already now, one numbers for telling us how good is the selectivity for the anion on cations, and this is a transport number. Transport number of the ions that can go across is defined as the quantity of electricity that is going across your membranes transfer with these ions compared to the overall quantity of electricity going across. Normally in a solution, 50% of the current is related to the ion positive and 50% of the ion negative, roughly. It's 50-50 or 48-52, etc. In a membranes, if it's still 50-50, the membrane is not interesting. But in a system that I was defining before, all the current going across can be related to the movement of the counter ions. So a good membrane, for example, anionic membranes, will have a transport number equal 1. That means all the current compared to the overall total current is transported by these ions, not 50%, 100%. And so transport number equal 1 means that we have a good ion exchange membrane if 100% of the current is related to the movement of the counter ions. Cationic membranes will be membranes in which 100% of the current is transported by the positive ions and not from the negative one. The same does not happen in solution, where 50-50 is the amount of current transported. So transport now will be 0.5, 0.5 for counter ion, co-ions. So we will define our selectivity at the end in terms also of the transport number, because that's giving an idea if the membrane is good or not. Keep in mind that membranes can be also bipolar. We can have a system for some specific application in which you can combine anionic membranes and cationic membranes. Membranes selective for anions, membranes selective for cations. And this kind of system is interesting in some cases, for example, for working with water splitting. You can separate, you can split the water in H plus and OH minus using system of this kind, and you can make the same with salts. So you can separate, sometimes you can split some salts and producing acid and bases in some chemical reaction. So this kind of configuration is becoming also interesting, and for specific wastewater treatment sometimes where you want to have this kind of operation, for example, this, having this water splitting or other salt splitting. We already mentioned a little bit about Donnan equilibrium, what it is, and which are the relationships that we have to remember a little bit. And we define for doing this in an ion exchange membrane that just separate two solutions of the same concentration or different concentration. We have to define the electrochemical potential. If you want to define the condition of equilibrium, we must have this electrochemical potential of the different species being equal at the interface between the membrane phase and the solution. Electrochemical potential is nothing more than the chemical potential that we learn to define plus the electrostatic potential, which is nothing more than the difference in electrostatic force and the Faraday constant for the charge of the ions. So that's what we define as electrochemical potential. and the zeta that we will use always is the charge of the ions. If we have a membrane and we have a different concentration across from one side to the other, and so we can have just a transfer of ions from one side to the other side, we will have, in this case, a gradient of the chemical potential and a gradient of the electrochemical potential if we are with a charged membranes. And the interface between the solution and the membranes on both sides, we will have, if there is a different concentration of the single ions in the membrane phase and the solution on both sides, we will have what we call Donnan potential. The overall Donnan potential will be the difference of the Donnan potential on one side of your membrane and on the other side. At the interface, we will have the Donnan potential between different concentration of the single ions between the membrane phase and in the solution. So what we call here Donnan potential is difference between solution on one side, the feed side, and the solution on the permeate side. And this is expressed, as we already saw the other time, through the ratio of the activity of the single ions across our membranes, minus this effect related to the driving force in the different on pressure, and this one we will call as a swelling pressure of the water, for example, present in the system. This is the partial molar volume of the components. The Donnan potential across our system can be just defined in this way, in which we have to consider the pressure of the solute in the solution and in the membrane phase. That is the case that we are considering. So we have the membrane phase, this species in the membrane system and in the solution at this single interface. This pressure that we are doing, we call swelling pressure. And swelling pressure normally is expressed as function of the water activity, and so you can rewrite introducing the water activity, and that has to be valid in the system for the species which are positive and the species which are negative. For the species we call cations, and for the species we call anions. So we have to respect electroneutrality. And that is the problem that is creating at the end the problem of the selectivity, the exclusion of the membranes, because we now know that we cannot have equilibrium if one of the charge cannot be counterbalanced for another charge. So the fixed ions cannot move. So if one ions of a charge opposite trying to enter, we are violating this, the equivalence of the negative and positive charge in the system. But anyway, the Donnan potential between the ions in the membrane phase and the solution, that means that each interface will be expressed by this kind of relationship, where again, remember that the activity, this is in the membrane and that is in the solution. The same here for what concerns the swelling pressure, membrane in the solution. And that's why we can rewrite the relationship between anion and cation now, between the positive and negative ion at the interface, and that will be the expression for the cation, and the same expression will be for the anion. And that's in a condition, in principle, to realize the electroneutrality, these two potentials has to be equal. Now, if you have a univalent, is a little bit more simple. If you have a not univalent electrolyte in your system, as you know, when you put in any solution any strong electrolyte, in principle, the strong electrolyte will be 100% splitted in positive species in the negative species. If the weak electrolyte, you can have an equilibrium, but the strong electrolyte, all the salts are strong electrolyte. So sodium chloride does not exist as a molecule in the solution. What exists in the solution is sodium plus, sodium ions, and chlorine ions. No molecules of natrium chloride exist in liquid phase. There is a strong electrolyte, totally splitted in this positive and negative charge. So you can rewrite for the principle for electroneutrality, you must have that zeta A for VA is equal to zeta C for VC. That means positive anionic and cationic species has to be in the same equal to not violate electroneutrality. From a mass balance, we can write here a mass balance. The total volume of the solute will be subdivide, as I mentioned, in anionic and cationic species, and obviously this mass balance equivalence has to be respected. So you can rewrite using this kind of relationship. In the previous one, you can rewrite your system, and you will have this kind of expression in which we still are working with activities, but we learned already that the activity are equal to the concentration through a deviation from the equality only. You can express through the activity coefficient. So you don't know normally the activity. What you know when you prepare your solution is the concentration. The concentration is related to the activity through this term. If the solution is ideal means relatively low concentration, you can have this gamma is equal 1. In other case, when you increase in concentration, you can have deviation from 1, and this can be 0.9, 0.8, 0.7, and this activity coefficient just give you an idea of the deviation from ideality. Remember that it can be just ionic strength we defined last time is a way to understand also the value of this activity coefficient. But anyway, assuming that we are working in an ideal system, that means relatively low concentration, you can rewrite this term in terms of concentration, which are more familiar, more immediate. And so you can rewrite your, if you are an ideal solution, your electroneutrality in terms of the equality between the concentration of the single ions in the feed solution, and in terms of co-ions and in terms of counter-ions in the membrane phase and in the solution. And the two relationship has to be valid. What is written here is the concentration of the counter-ion, that means ion with charge opposite to the fixed charge of the polymer, forming your membranes. The CO is the concentration of the co-ion, remember, which is ion with the same charge of the fixed ions, not the mobile, but the one fixed in the matrix of the polymeric membrane. And in this case with CF is the ionic group fixed on the polymer matrix, the one that cannot be moved. You can again rewrite the relationship in terms of concentration, and you will, and assuming that you are working in ideal system, that means in ideal solution, the very low concentration, you can assume that in our system, the concentration of the co-ions in the membrane phase is much, much smaller than the concentration of the feed charge. Otherwise, this is not ion exchange membranes. So assuming that we are in this situation in which this kind of relationship exists, otherwise all our discussion, not on an exclusion basically, but in this situation, when you have high charge density, a lot of fixed ions, and relatively low concentration of the co-ions, that means in this situation, dilute solution, we can, this kind of relationship is valid, and you can just arrive to the kind of relationship we wrote last time, which is the important one. That this relationship is telling you, when these assumptions are valid, that the concentration of the co-ions in the membrane phase, the one that can penetrate, basically can be very, very low when the ratio between the concentration of the same co-ions in the solution compared to the fixed ion is relatively low. When this number is high relatively to this number here is very, very low, approaching 0. So that is the relationship. And if you assume that we are in ideal solution, these terms are equal 1, and that means this is the expression I wrote to you last time. Okay? Remember that the deviation from ideality is present with the square here, if you make your analysis, which means that when you are increasing concentration, if you are approaching a situation in which this kind of relationship is no more valid, the deviation it can be significant, because also the deviation from the ideality is affected by a square of the value of the activity coefficient. But in principle, this term you can neglect, and that is the relationship. That means that if we are working, for example, I just told you last time, I like to repeat, with the new system today, for example, if you want to produce energy using reverse electrodiode, we'll see what we are talking about, we need system. You will see we will concentrate the solution. Seawater is relatively diluted. We will work 5 molar. 5 molar if you want to work at 5 molar solution, you need a very high fixed charge density in your polymers. Otherwise, this effect will not be significant. You need only this number bigger than this. If this one is a 5 molar, this one has to be more than 5 molar. And that is not easy. When you prepare a polymeric material with such a high charge density, you can have, for example, a lot of swelling, interaction with water, and that means decreasing mechanical properties. You dissolve your membranes, and that is affecting the overall system from a mechanical point of view, not for electrochemical point of view, but that is the same story. The membranes don't work. So we have to take care of this. One of the application of this kind of system, the easiest one and the first one, application of this kind of problem exists in nature. Our body is full of membranes that are selective transfer of ions based on this mechanism. So in fact, the Donnan was a biologist, was not a chemical engineer or a membrane engineer. These people were biologists, and they have been learning about this kind of phenomena without understanding the origin of the phenomena. They had no idea about charged membranes and transporting membranes, etc. But they were observing the fact that with some biological products, there was no possibility to penetrate with some salts, and some other one were going across. It was they called Donnan exclusion at that time. Today we know this story. So this problem, these systems are not new. They exist for a long time. What is new is the fact that engineers decided to try to utilize the properties of this kind of material, when this kind of material people started to produce as membrane, in different applications. The initial application was not desalination, it was just the opposite. Not too far from here, in Japan, people were not. I told you that chloro-soda process is a basic industrial process for starting any other industrial production normally. So you have to produce sodium chloride, basically, which is the salt from where you produce chloro and soda. In Japan, where there was a strong industrial development years ago, they had no big sun, no natural energy available, so they were trying to produce sodium chloride from the sea. Not easy. In Europe, in Italy, we produce just making big ponds and look into the sun, and the sun evaporates the water, you produce huge amount of salt. We call it saline, place where you have we have city called saline, because they just produce salts, just using, taking profit of the intensity of our sunshine. Not in Japan. The first application of these membranes was to produce salts, basically, to remove water from the seawater and to concentrate the salt, not producing water, as we are doing today, but produce sodium chloride at high level concentration for starting chloro-soda process and producing chloro and soda. Because imagine that you have one membrane that is cationic and one membrane that is anionic. And if you now realize this system, here you put your electrodes, and one electrode, in one side you have a positive charge, the other one would be negative charge. So you're creating an electrical field here. So now if you have in one, so between, and you have some spacer that separate one membrane from the other. So the solution can move here. You can enter with feed water, with seawater, for example, and on this compartment, in this compartment, etc. Now, what happened here? We have been creating a difference in voltage. So the ions, if you are entering here with seawater, you have a positive ions and negative ions. Sodium chloride does not exist. You have sodium ions and chlorine ions in the system. Now, the positive species, sodium, will just migrate in this system to the negative electrodes. So it's moving to this compartment here. The chlorine, negative charge, is moving to, will be attracted to the positive compartment, to the positive electrodes. So you have a migration phenomena for which one species is moving in one direction and the other species with the other charge in the other direction. So we are removing positive ions and negative ions in this compartment. Because in this way, what is happening here, that if this membrane is cationic, the positive species will go across. Assume here transport number equal 1. all the electricity that is moving the system is moving across these membranes. On the other side, chlorine ions will find anionic membranes and they will go across. So no problem. We are removing positive and negative using the selectivity of these two membranes. In this other compartment, what is happening now? In this other compartment, if we have negative ions and positive ions, these positive ions here will try to migrate in this direction. But here we find a membrane which is anionic. Transport number 0, they cannot go across. The same in the other direction. They will, if you have negative ions going in the other direction here, they will find a negative membranes, 0 transport, so they cannot go across. So what we are creating here is a system which here we just remove the salts, and here we cannot remove the salts. We just, the water would stay there. So we accumulate we extract the water in one sector and we concentrate on the other one. And that is the way of doing. So what is happening at the end, that in this kind of compartment, we entered with seawater and we are now diluting the solution. We are just leaving only we concentrate the solution in this compartment here because we enter with the ions and they concentrate, and the other one we are diluting because the ions are going out. So we dilute all these compartments, we concentrate in this compartment, we dilute again in this compartment. If you now you can put together all the dilute solution going out in a pipe and all the concentrate solution in another pipe, you had on one side you are producing brine, which means you are concentrate salt solution, and on the other side you are just producing water. Today we are using this system to produce water. You can remove salts from the seawater just using this concept. So these ions are going on one side and the other one, and you just accumulate the ions in this compartment. The ions here penetrate, but they don't go out again. So just have concentrate on this side and dilute. The Japanese were using this one, the concentrate solution, as a brine, and we are using today the dilute solution as fresh water, basically. This is very important. Everybody of you is dependent from this. If you have some mama here that is giving milk to the children, and, very often the children don't have directly milk from the mother anymore. You buy milk for baby in the pharmacy. The milk that is produced in the pharmacy, which is not from human beings, is from animals, it has to be treated to approach as much as possible the quality of the milk of the mother. And the quality of the milk of the mother is a different concentration of salts. If you want to solve the problem, all the milk that you are giving to the baby today is produced in this way, because this is the way in which at room temperature, without increasing temperature, so you don't have to remove in other way that you can destroy some of the components, protein, amino acids, etc. You can at room temperature remove the excess of ions. For example, there is more potassium than sodium in the animals, in the cows, than what we have in the natural system. It's done in this way. So most part of the artificial milk is produced through membrane operation, in which you selectively remove some salts that you can just approach as much as possible the same concentration that you have in natural products. So that gives you an idea of what can be done here. You can separate selectively depending from the perm selectivity of the membranes, removing the ions from any substance where you want to keep concentration at a certain value. So this is basically the electrodialysis, and we will see that this system is useful in this way. When we apply now a difference in electrostatic potential, we give some energy and we have the ions moving across. We have migration, diffusion and migration of the ions in the system, migration in electrical field. We can use the same concept as reverse electrodialysis, doing the opposite, when we don't apply any electrical field here, but we apply a big difference in concentration between this species and the other one. We put water here and salt here. So in this case, we have diffusion. We create a difference in concentration. Ions can migrate in the same logic due to the difference in concentration, And in this case, we will accumulate cations on one side, anions on the other one. We induce this redox reaction, oxidation reduction, and the electron that we are producing will go across. So in this case, we create energy just instead of using energy to migrate, to move the ions. If we have high different concentration, by diffusion, we can just move the ions on one side and the other in the same logic. That will be reverse electrodialysis. These systems are quite complicated. If anybody is going to be involved in this, remember that there is a lot of phenomena not related to the membrane itself. The membranes we understood in principle has to be very selective. That means transport number of the cations or the anions in the two different membranes has to be as much as possible equal 1, such a way that there is only transfer of single ions across. But that is not enough. If you have this membrane available, we will see that the efficiency of the cell that you are going to create is very much related to the engineering of this system, how you build up this. Because this is a system which you have a lot of phenomena. You have just diffusion between anodic and cathodic compartment across your membranes. After you have migration due to the electrical field. After you arrive to the electrode compartment, you have a transformation from ions, oxidation reduction with production of electrons. So if you know that you are moving the kind of electrical conductivity from kind 1 to kind 2 to kind 1, from ionic to electronic. So all these phenomena together. And the phenomena are very much related to the concentration where the phenomena take place, at the interface between membrane and solution or the interface between electrode and solution. So we have a lot of interfacial phenomena, boundary layer phenomena, which really control the efficiency of the system. So the problem is much more complicated than the reverse osmosis, for example, because there is a lot of interface where concentration polarization, eventually thermal polarization, and other kind of ohmic resistance you create are quite significant. For example, the cationic and anionic membranes, they has to be a little bit separate. So you have to put a spacer in between. And these spacers are quite effective because depending from the design of the spacer, you can keep the concentration profile uniform or not at all. You can have interfacial phenomena. Interfacial phenomena are concentration polarization phenomena. They kill the process as in reverse osmosis, as in nanofiltration, as all the membrane operation. So the design of the spacers is quite important, and today engineers just working how to realize how to move the solution between all these membrane systems. When you realize one of the system is not 1 or 2 or 3 membranes, the stacks are 1,000, 5,000, 20,000 membranes packed together as much as possible in a small space. In each one, when you make the calculation, you calculate for each one of the system, and after you have to multiply for 10,000, assuming that each one has the same performance, because the systems are in principle modular. So it's quite important how to realize a situation in which the efficiency, that means the concentration at the interface, are equal to the concentration in the bulk, in which there is no additional resistance, no concentration phenomena, no boundary layer. And that is basically related to the design of your spacers. They can have is a system in which you can induce a turbulence, so you can increase the efficiency without spending too much in energy. So this is an important part of the story to be considered. When you can do this, at the end, you have a huge plant. You can realize, as in reverse osmosis, all these are thousands and thousands of these single cell packed together, and that is, for example, is I think just in the dairy industry, and this is cell in the lab. Also in this case, you see this is the units, but in here, between these two cathodic, anodic, cathodic compartment, there will be at least 30, 40 different cells packed together with the membrane in between anionic, cationic, and the spacers. So that is, and that can be multiplied and becoming huge as we discussed in reverse osmosis. If you want now to analyze the system and to which are the parameters we have to keep control, the overall mass transport in our system is given by, if you have for a single ions, these flux across will be, as we know, will be proportional to the gradient in the electrochemical potential. So we can express our electrochemical potential in terms of these chemical potential gradients and the electrostatic potential gradients. And that is in a solution, ideal solution, as we saw before, activity and concentration can be the same. We can rewrite in this kind of expression. And at the end, the total, these are ions, these are electrical charge moving, so we are creating an electrical current. The total, the intensity of our current would be nothing more than the I, that the addition of all the contribution to the current that could be given from all the ions moving with their charge. So that is the expression of the current intensity that is crossing our cell, related to the single ions moving across. Remember, this ion can be part is positive, part is negative in the solution. In the membranes, this current intensity is given basically 100% to the ions with the same charge here. This zeta will be zeta plus or zeta minus. In solution, the same addition will be zeta plus, zeta minus, 50% on one side, 50% on the other one. That's the big difference between the membranes are inducing. So that is the expression now. If you substitute the expression of the flux in this current, in the current intensity, that will be the expression of the current intensity. So the gradient of the electrical potential, the phi in the x, is nothing more than this term here and the term that is here. So you can solve the expression and make the substitution. You have a kind of expression of this kind. Not really important for the moment. You can now, this expression, by the way, I'm just wrote down here, because now we can try to rewrite this expression introducing the term that I was defining before, which is what we call transport number. Transport number is nothing more than the fraction of the current just related to the flowing of one of the different ions which is present. So transport number can be all the current transported from the species I compared to overall current that is going across the system. Zeta is the charge of the ions. In this case, if in a solution, this transport number normally is 50-50 for cations, for anions. In the membranes, what is happening is that the amount of electricity transferred across the membranes is basically 100% related to one of the ions. Not the other one are excluded. Non-exclusion, they don't enter. So, and they are positive or negative. That means, so we can have a transport number 1, cationic, good membranes, cationic membranes, transport number 1, anionic, good anionic membranes. Okay? That's one of the numbers. We can also define these ionic transfer numbers, which is the number of mole of the ions I carried out for 1 mole of electrons. So just a little bit different definition, but basically the concept the same. And that is the one that trying to remember, because that's the one that can make sense. Now, if you just use this definition, you can introduce transport number in the expression of the ion flux across the system, and for a simple case, make a 1,1 monovalent salt, sodium chloride, potassium chloride, what it is. So you can just rewrite the equation, introducing the transport number in this system, and the case of the fixed charge don't move, so they don't contribute to any current, and so that the transport number for these fixed ions in solution is 0, and vice versa. For ideal cation is 1 for the cations, and for ideal anion is 1 for the anions going across. So that is the definition we have to remember. Keep in mind that ions never move by themselves. Each ion in a solution is always surrounded by a certain number of molecules of water. The single ions don't exist, basically. This molecule of water can be 7, can be 14, depending from the situation in which you are working, but there's always some water moving together with ions. And that means that in the overall system, you also have to take care when you make, and that change the mobility of the ions, because if you move a single ion, it's a certain size. If you move an ion with the all the water molecules, the solvent, the ions, the mobility can be different. So when you make all your calculation to define the phenomena that is taking place, you have to consider also the amount of water that is moving across, bounded to the single ions, positive and negative. And so you can also create some gradients of osmotic pressure between diluted and concentrated solution, and also the ion transported related to the single ion that is moving. So that is one of the problems we have to consider. The flow of the solvent in our membranes can be just related to the different concentration, but part is related to the hydration of the ion. So basically, when if you want to be more accurate and you're writing your transport number, you have to take care of the situation of this water. So the ion exchange membrane, you have a transport number also related to the water, which means the amount of water related to the amount of the number of mole of ions that are moving across. So part of the water is just moving together with the ions. And these numbers sometimes are not marginal. Another number you can define is the perm selectivity of cationic or anionic membranes, the same expression, in which you have this perm selectivity, which is nothing more than the transport number in the membrane phase of the cations minus the transport number in the same ions, cations in the solution, related to the transport number, the amount of electricity going across, of the anions. So you know relatively how much of the cation, how much the current is transported by the cations compared to the current transported by the anion. And that is giving you an idea of what you call rejection in reverse osmosis, perm selectivity in ion exchange membranes. Again, perm selectivity tends to 0 when the transport number to them is equal to that in the electrolytic. When they are 0.5, 0.5, 50%, 50%, this number here is basically 0. There is no selectivity in the system. The membrane don't work, basically. Remember that the membrane don't work also in situation in which the fixed charge density is not higher than the concentration of the solute. So you can have a membrane that works very nicely with a nice perm selectivity for a certain value of the membrane is fixed, has a certain charge density. Now, if the solution that you are working is relatively diluted compared to the fixed charge, this number will be high. But if you are increasing the concentration of the salts, what we are doing today, because we want to increase power density in reverse electrodialysis, or also in this case, if you have very high brine solution, this number tends to 0, also if the membrane is good. Not because the membrane is bad, but because we are increasing too much the concentration of the solution. That's one point. The other one, remember that also as all membrane operation, we have a fouling phenomena in this system. And the fouling is another, the mechanism of the fouling in this case is different. It's not just blocking the membrane, etc. It can also happen, but that's not the worst. What can happen is that some ions present in the solution, they can be attracted, for example, from the charge fixed in the membranes, though they will neutralize charge density. That's happened particularly in anionic membranes. Cationic membranes are more easy to handle. Fouling, this kind is not, you know how to control. In anionic membrane, we still have this kind of phenomena for which you decrease the charge density in the membrane because some of the chemicals present in the solution interact with the fixed charge, neutralize the fixed charge, and so decreasing charge density, and that means decreasing the perm selectivity. So always we have to take care of this, and that is not easy to predict. It depends on what is in the solution. If in the solution is something unexpected that you have not been able to separate before, etc., this big fouling on the ion exchange system that you have to take care. However, this is typical fouling, but traditional phenomena that we have been already discussing are taking place also in in electrodialysis with ion exchange membranes, as in reverse osmosis, as in nanofiltration, as in ultrafiltration. And we have typical concentration polarization, which is related to one parameter we have to remember always, is the limiting current that we can produce in the system. And the limiting current that we can produce in the system, phenomenologically is clear what does it mean. If you have a system in which all the current is transferred by positive and negative ions from one side to the other side of your cell, and suddenly we put a membrane inside, in these membranes, most part of the current is transferred not 50-50, but 100% for our single ions. What is going to happen is that at one point, these single ions arrive into the membranes. They arrive with 50% of, in a 50% amount. Suddenly, they go 100% across, so the concentration is going down. To the point, at one point at the interface, you have zero concentration of the ions that you want to transfer, because you have to supply much faster than what is normal supply. The supply normally is 50-50. Across the membrane, they start to run 100%, 50% more, so you have concentration decline to the point that the concentration is zero, so nothing is going across. So you are increasing the ohmic resistance of the system a lot. So that is the limiting current. When you arrive to this point, you are approaching zero concentration, the interface, that's a limiting current. You must be careful, because if you want now having something going across, instead of increasing pressure, you're increasing the difference in potential. You're trying to increase the electrical field. Be careful, because if you do this, and people have been doing and trying, what is happening now, you have another negative phenomenon. You have water splitting. If you give too much energy to the system, the molecules of water, they split, and then they split, you change pH. You change the concentration of the hydrogen ions, and changing pH can change completely the behavior of your membrane, to the point they can destroy the membrane. Membrane polymers can be polyelectrolyte particularly, are very sensitive to the ionic strength and to the pH of the solution. So if you have water splitting at the interface, because you're trying to move the ion across, increasing the potential difference between the electrodes, you can eventually improve a little bit the system, but you can kill chemically the process, because the water splitting destroys the polymer, the polyelectrolyte you have been using. So there's a lot of trouble that you have to take care. Limiting current is determined by concentration polarization phenomena at the membrane surface in the diluent compartment of your system. What is this? You have a mass balance that you have to consider in your system, in which you have the flux of your ions in the membranes is given by the diffusion of these ions in the solution related to the gradient concentration, and to the migration of the same ions in the solution related to the electrostatic field that is moving positive to this negative compartment, negative to the positive compartment. So you have diffusion and migration. And the addition of these two terms is the flux in the membrane surface. So that we have diffusive and migration flux in the boundary layers are the two ones that we have to control. The total flux of the counter ion, consider just the counter ion, is given by the transmembrane transport numbers of the counter ion in the membrane phase related to the overall current intensity divided the Faraday and the charge. So this is the relationship that we have to consider. Now, what can happen that in your system, the migration and diffusion are given by the fixed law expression, by the electrical flux transport number, which is current divided the Faraday and the charge. If we combine everything, we will have at the end this kind of relationship where the overall current intensity is related to diffusivity, gradient in concentration, that is thickness, and that is the difference of the two transport numbers. So if these transport numbers, if this is 1 and this is 0, this is okay. But if this 1 and 0, if this number disappear, the current density is going to 0. So if you just have the limited current that you can define is the current for which the concentration at the interface is going to 0, basically. And that happens because 100% is the transport number of this ion in the membrane, and 50% is the one that we can supply through just from the solution to the interface. And that is what is basically happening. So we can have the maximum current density, what we call, so the limiting current is the maximum current density we can realize is reached when the sole concentration of the membrane surface in the dilute cell becomes 0. And that is for a certain intensity of the current, that is the limit 1 is 1 is term go to 0. So that will be the expression that we have, which is related to the two transport number that we have in the system. And that is what happens. If you do the experiment by yourself, and you're looking what happened, and you plot the current density in your system as a function of the voltage difference between the electron in your cell, you will see here that increasing the voltage, you are increasing current density, because everything is working, but at one point, you arrive to the limit in which, and from this point on, this current density basically, here just the resistance is increasing significantly. After the limit current, the electrical resistance increased drastically. And so that's because we have been approaching this value of the limited current. And that is a clear phenomena. And to avoid this, what you have to do? You have to find a way to supply more ions to the membrane surface than the 50% that the normal transport number was giving. So you have to create a turbulence, you have to study appropriate spacers in which there is no, this boundary layer can be destroyed, you can mix better, etc., which costs money, by the way, because you have to have a pump that will move the ions across, etc., but that is the way of doing. So otherwise, we can have a high, incredible high level of increasing the resistance. What is now reverse electrodialysis? Reverse electrodialysis is not very much utilized at industrial level. You can also use it in some kind of industrial level. But today it's becoming very popular because it's one of the forms in which we can realize the dream to produce energy taking profit of the difference of salinity gradient, not just in your small battery or in the fuel cells, but at global level, mixing seawater of the ocean, huge amount of water, full of salt, that means with very high Gibbs-free energy, compared to the one of these freshwater, river water, they meet in many, all around the world, at the interface when the river is entering the sea. That was the origin. Today, you can realize this kind of this same approach also in different way, on purpose. You can utilize, you can look, for example, to utilize the brine of big desalination plant, a very high concentrate salt solution, and mix with seawater in some case, and creating this interesting system where big difference in Gibbs free energy is available if you have membrane. Because if you don't have membrane, you mix, nothing happens. You dilute the solution basically, or you concentrate depending on what you're doing. But if you put a membrane inside, you can realize osmotic phenomena basically, and you can produce electricity. What you can do here is just having seawater and river water. What before were just seawater and fresh water, exactly the same, but don't apply any voltage at your electrodes. Just have the system working by itself. What is happening here, that if you have a very high concentrate solution on one side and fresh water on the other one, we have a different concentration, so you have just diffusion, fixed diffusion across the system. So we will have some species that will move, -1 will go to the positive compartment if the membranes will be permeable to the -1, if the membranes will be appropriate sign, anionic or cationic. Vice versa, on the other side, you will have positive species moving by diffusion under driving force with different concentration on the other side. And they will move and if the system is working correctly. So also in this case, we are creating a concentrate. At the end will be high concentration of negative ions in the cathodic compartment, positive ions, or sorry, vice versa, positive here and negative here. And now here you can induce chemical reaction. Normally here you have a solution of iron bivalent, iron trivalent, so a redox reaction, such a way that this high concentration of salt that we have been creating, just oxidation or reduction is taking place in this compartment, and we are producing electrons. And these electrons now will go across, and you just switch on your lamp. So instead, in this case, instead of creating a difference in voltage for moving the ions, you take profit of the different concentration, and the different concentration will create different concentration in the anodic and cathodic compartment, and if you induce chemical reaction taking place, having your catalyst and having your species oxidation and reduction, you are producing the electrons, and on one side you produce electrons, the other one you absorb the electrons, and you are moving the current across. That's exactly what happened in the other system, as in our cell, etc., but you can do just using seawater and river water, for example. If you use seawater, river water is interesting, but not enough. In the sense that the voltage that you can have for a single cell, the overall power density you can create will be done by the number of cells you have. Single cell will give a certain power. If you multiply the number of the cell for the power of 1, assuming they are all working the same way, you will have the overall power of the system. Today, if you're just using river water and seawater in the system, the power density, that means watt per square meter you are able to produce, is relatively small. Can be of the order of 0.7, 0.8 watt per square meters. Interesting for writing publication, becoming professor, etc., but not interesting for solving the energy problem in the world. If you are able to improve the system, for example, instead of using seawater, we are putting here brine water. Instead of having here 0.6 molar, we put 6 molar, not 0.6, 6. That means 1 order of magnitude higher against eventually freshwater, river water. So the power density is no more 0.61 watts per square meter. Can be, for example, some numbers that here in Korea or in Japan are suggested is about 21 watts per square meters. With 21 watts per square meter, if you build up huge power station, that's becoming quite interesting and competitive. But for doing this, you need membrane that can work with 6 molar. And we learned before, 6 molar can be too high for a Donan exclusion. So your transport number is no more 1, can go down. So you have to produce better membranes that can operate in such extreme condition, and that's something that is not so obvious. Plus, you have to control all the different additional resistance, concentration polarization, ohmic polarization. Here in this case also interfacial phenomena, what is called overpotential. There's overpotential that can reduce the capability to oxidize or to reduce your ion, etc. So all these phenomena together make the system quite interesting but quite complicated. If you want to predict the numbers, now that is the theoretical value of the potential across your membranes, for assuming again a simple source, the sodium chloride, is just given by a very simple equation that is familiar to all of you. It's the Nernst equation. The Nernst equation is giving you the difference in the voltage you can realize in a cell of this kind through the difference in concentration of the cations in the system on one side and the other one. So that's the Nernst equation, that the theoretical one that you have to consider. Though that is assuming that the membrane is 100% selective, and we learn number transport equal 1 for the cations. Now we know what does mean selective in this case. The other numbers are the traditional one. This R is the universal constant of the gas, temperature, and charge, Faraday. And you can just put your concentration, the activity solution, and you can calculate. If you do this for fresh water, this order of magnitude of concentration, seawater, 0.5 molar, you can have basically a voltage difference of about 80 millivolts. This is what you produce with the Nernst equation is giving you. If you change this concentration, you change these numbers, and you can have much more than this 80 millivolts. That is the point. The total potential that you can produce, obviously, is the addition of all the potential difference for each pair, for each cell, for each pair of membrane that you are utilizing. That means if you are able to realize a system, complex system with thousands and thousands of these membranes all working in a nice way, keeping the concentration at the boundary layer all the same, etc., this system is becoming of interest. That is the equation, the relation between the salt concentration in the two compartments, and depending from the temperature selectivity is given from this relationship, where this term here, that is the average. No, we don't have all the membranes basically with selectivity equal 1. So you have to introduce, in the previous equation, we were expressing this term, assuming that selectivity is basically membranes are ideal. There is no transport number is 1 for cations or anions. If you want to be more realistic, you have to correct the equation, introducing this term here, that is the average membrane perselectivity of an ion cation in your system. And this is all the other terms are the same, but this is making the process more reliable, more real, and this is the point. You have also to consider the stack resistance as, again, the resistance of all the different cells, the single compartment you are using, and that is so you can just realize this kind of, you have this kind of expression giving you the total resistance in the system, which is the one of the anionic and cationic, and that is the effective area of your membranes. This RAM is the resistance of the anodic, this cationic, thickness of the concentrated compartment, thickness of the dilute compartment, etc., etc. And that is the K are the conductivity in different compartments. So that means each one of these terms can have an effect on the overall voltage and overall resistance. So you have to know in all the system which are this term can change related to the boundary condition for each one of the membranes. That's, we learned already that the limiting current can be one of the problems and so on. So at the end, if you want to calculate the overall final power output of your stack in reverse electrodialysis, you can just utilize this Kirchhoff law, that is traditional relationship between the power density power that you have in your system with the resistance and the load that the system itself, and the maximum power that you can produce, the output of this system, has to be at the best can be equal to resistance of the stack. That is when this the resistance of the total load resistance is equal to the resistance of the stack, you are in the best condition of power output you can realize in the system. And that is very much related to the flow dynamic, nothing to do with the membrane itself, but to how you realize your system. In this case, that is the equation that you can utilize in this condition to calculate the maximum voltage, the maximum power that the power density I was mentioned before you can obtain, which you can see depend from the resistance of each one of the membrane, from the conductivity of all the boundary layers, from the size of the boundary layer, etc., which are, again, have nothing to do with the membrane itself, have to do with the engineering of the system, and that's why you have to realize at the best this kind of condition. And that's why people are spending today a lot of energy and money in trying to well design this, how to put together your membranes, assuming that this one are 1,000, 10,000, 100,000 cells, single cell that you have to combine in one. And then you can see here you have again the cathode, you have the cationic, the seawater compartment, anionic, river water compartment, cationic again, etc., and not so simple, but huge dimension that is not so easy to be realized. And today in the literature you can find a lot of membrane already existing, both cationic membranes, anionic membranes, and that can be utilized industrial level with interesting perm selectivity. You can see the number here are very much approaching the ideal value, 98.6. They are not 100%, but still 97, 98, 90, and 99 basically. These elements are one of the most traditional membrane people are using. And Fumasep are produced in Europe, in Germany. And so these are quite interesting with different thickness, different resistance, etc. And these are just the membrane that are, each one of them has some specific property, so you can use in different applications. You can see here people are using for diffusion dialysis of acid. They are using, they are resistant against organic fouling. There's a lot of interest today also in this kind of system to utilize not only fresh water, but organic solution, where you have to extract, to remove salts, or to utilize for this reverse electrodialysis. So membranes of this kind are under investigation, and what you have to try to realize is high permeselectivity, high transport numbers, and low electrical resistance, ohmic electrical resistance. That means and good mechanical and stability, and high in general chemical and thermal stability. Obviously, if you increase temperature, you increase diffusion coefficient, and that is positive. You decrease viscosity, is positive both for the ions diffusion and ion migration. So both terms have a positive influence, but in this case you need membrane that can stay high temperature, which is not so obvious in case. Here are some of the results that you can obtain if you just want to do some experiment from yourself. So you can see that perm selectivity, for example, as I was mentioning before, can be as a function of the charge density. Changing charge density, now we know why, because changing the charge density, we can have a situation in which the transport numbers are no more 1, because Donner exclusion is not working 100%. And so as function of charge density and of the concentration of the solution that you are considering, you can have a different value of the perm selectivity. In some cases it can be high, some cases cannot. For anionic, cationic, the numbers are split, and there is no linear relationship because that depends very much for the interaction between the charge density and the property of the solution you are treating. But people are working in terms of perm selectivity, in terms of resistance, specific resistance of the system, and again you can have for cationic, anionic distribution, different value depending on the kind of membrane, and etc., etc. In general, membranes have relatively low fixed charge density, have also a lower selectivity because the co-exclusion phenomena is relatively less efficient, and we learn why. The equation we wrote now, if we have a relatively low charge density, we have the possibility that the Donner exclusion does not work as expected, because the solution that you are working can have a similar value in concentration than the charge density of the membranes. And so the effect can be more, or just because also if the initial solution was low in concentration, you can have phenomena at the interface. You can have increasing of the concentration or boundary layer phenomena, and that will change completely the performance of your membranes. So that's a typical, that's why you prefer to operate with a high charge density, but high charge density can have decline in mechanical properties, and so you have to solve the problem. And normally cation exchange membranes have a high charge density, and they are the best one, as I was mentioning before, than the anion exchange membrane. Anion exchange membrane normally are less effective. We don't have very good one for this kind of phenomena, plus fouling, possibility of interaction that neutralize some of the charge and decrease the perm selectivity, basically. Very high concentration of fixed ion charge in the membrane lattice can give a low electrical resistance, but you have the swelling, as I mentioned before. So this is one of the phenomena that you have to keep control. If you're now trying to understand in general, you can see here that the power density as function of perm selectivity resistance can be quite effective. You can have changing the spaces, changing the assembly of your system, going from 600 micron to 150 micron. You can have very different value of the charge of the power density as function, for example, of the perm selectivity. And that is not related to the, without changing the membranes, it's related to the difference to the spacer. That's related to the concentration profile that you are going to create. The membrane resistant perm selectivity are of minor importance when thicker spacers are used. If the spacers are becoming thicker, this effect, this resistance perm selectivity are less important. But if you are trying to compact more and you have very thin spacers, the problem of the control of the interface is becoming more severe, and the membrane property do play a role in the large increase in power density up to value 6, 7 can be obtained at low membrane resistance and high perm selectivity. So this effect of the thickness, thick spacer or thick spacer here, but from 600 going down to under 50 can be quite effective for having the value that you have. Here are some of the values that can be summarized, but these numbers, these are relatively new numbers, by the way, and you can see here if there is the overall, the watt per square meter, the power density expected and predicted is a relatively good agreement. And however, these numbers are interesting number for single cell, etc., but not very much for industrial application. With this number, it's just you can only make publication. The power density depends also very much as I was mentioning before, not only from the behavior of your membranes, but also the redox material that you have, which you are using to create the interface, the production of your electrons during oxidation and reduction. And so depends very much from the redox material, concentration of the redox species, and the number of these cell pairs. So depending from the kind of redox process and the electrode that you are using, for one of the most traditional, this one, is iron trivalent going to bivalent. You can reduce on one side, oxidize on the other one, but the other one you are cyanide also, or just water. Here is power, maximum power that you can realize depending from each kind of reaction, because this is what we call solver activation over potential. Some of the problem which happen only during the oxidation or reduction at the electron compartment, and that is you can change for each kind of reaction, and you can calculate, you predict the maximum power density for the single cathode and anodic compartment you are able to produce, depending also from the area that you have on this anodic and cathodic compartment. Here again, evidence of the effect of the spacer, the thickness of the spacers in terms of power density. You can see here how significant can be the decline of the power density in increasing the thickness of your spacers, and both in homogeneous and also in heterogeneous system, quite effective. Relatively thicker spacers are used, different power density for the various type of membrane is marginal. The effect of membrane property become prominent only for thinner spacer. And that is obvious because in the thicker one is much more easy to control boundary phenomena, which is becoming much more complicated when you have a very thin spacer here. The other effect that is quite important, and for example, that under study today, if you go in literature, you will find a paper from our institute, from ITM, where seawater is a complicated system, it's never sodium chloride. At least you have different bivalent ions, magnesium, for example, a lot of magnesium, a lot of some barium, some strontium, etc. So the effect of the ions is important. It's important also because I mentioned it before, we have a lot of transport of water in the system related to the single ions. And bivalent have a different, different amount of water in their clouds, and this effect can be interesting. And you can see here that the stack resistance, for example, is changing depending from system which you have only sodium chloride or when you also have magnesium chloride. Here the effects are not too big apparently, but this effect can be significant when you multiply for all the number of cells that we are considering. So one other part of the analysis we have to do today is the effect of the multivalent ions on the overall resistance of your stack, which means the power density that we can have at the end of the system. And here the same effect of the multivalent ion on power density generation. You can see here that is the power density as function of the ion flow paths for a certain kind of membranes that you have to also to measure this geometry of the system, because it's a question of the flow dynamic, and there is a quite significant effect, much more depending from if you have magnesium sulfate, sodium sulfate, chloride, magnesium chloride again. You see there is a quite interesting difference in the internal resistance of the system. So all this effect has to be carefully analyzed, including the ratio between saline water and freshwater flow rate. I mean, the two different in comparison, because we are changing the boundary condition and we are changing the concentration profile at the membrane interface. Fouling, as all the membrane operation, exists in the same way. We have a fouling reverse electrodialysis, and people working on reverse electrodialysis, we are optimistic, telling that we have less fouling than in RO, which in part is true. We don't have any pressure. So you don't have convection to the membrane surface. So we don't tend to accumulate by convection. So in principle, we can have less traditional fouling, but we have a new form of fouling. For example, I told you you can have fouling related to the interaction of some of the chemicals with the charge density of your polyelectrolyte, which does not exist in reverse osmosis or in PRO. So when you say make this comparison, no, that's what we are doing, because we say we have different form of fouling that we don't expect what people are normally used to find. But if we know in detail, we have to add here kind of fouling related to the decreasing of the membrane perm selectivity for specific interaction of some of the components of the solution with the membrane charge density. And people are not aware of this. It's very difficult to evaluate, and it depends from a lot of chemistry that still is under investigation. So that's one important. But in principle, you don't have convective flux to the membrane surface, you don't have compaction of eventually having deposit, so it's a little bit better. However, as I was telling before already, ion exchange membranes are most sensitive for organic and colloidal fouling. This is organic. If anybody is inventing membranes having at least the same performance of the cationic one, is already big progress. Today, all the anionic membranes on the market have this problem. We can foul, that foul in this case is decreasing charge density, decreasing transport number due to some specific interaction that we can have in this system. And okay, depending from what you are working, you can see you have a lot of difference between the expected power density and the power density that you measure in the single system. The theoretical one is up here, and what you're just measuring here, depending from the kind of space and the kind of membrane you are using, can be quite significantly different. Only one mention to one technology that exists in this department. This is quite interesting. No, I don't know if anybody here is working with the impedance spectroscopy. Is anybody here working on impedance spectroscopy here? No one of you. Anyway, you have in this department. You are using a different form that we are using. And if I can give you a suggestion, fouling is a problem number one in most part of the membrane operation, both pressure driving or electrical field driving. In both cases, this kind of technology can be of interest. Is born, and people are using today, basically if you are working in a fuel cell, in electrodialysis, etc., in ion exchange membrane, but can be also very interesting in normal system. This is nothing more than measuring ion conductivity of your membrane, ion exchange membranes. We want to have as much as possible low resistance of our system. So we have to measure the ion conductivity, is one of the parameters that we measure normally. You can measure by direct contact. You can put two electrodes and you can apply direct contact, and you apply the Ohm's law, and you measure the resistance of your stack, which depends from the ion exchange capacity of the system. That means number of ions going across, etc., etc. And this is direct contact. And that's what you measure in this case is the overall resistance of the system. You put in your number all the resistance present in the system. If you apply not a direct contact, but a certain frequency, alternate current, system is quite different. In this case, you measure impedance, and impedance there is virtual and real part, there is a virtual one, etc. It's a little bit more complicated. But at the end of this story, what is important? First of all, this typical plot where you can have this the proton conductivity. That's what you want to measure. Proton, in this case, is for fuel cell experiment where you want to measure have membranes only selective to proton ions. Some of you is working on this here in one of the labs. You are doing the same. And you are using also this impedance spectroscopy. So you measure different frequency, the proton conductivity as function of the membrane thickness, the membrane surface, and you can measure the membrane resistance as results of your analysis. So this is what you don't know. And if you measure this and you know this and this, you know the thickness, you know the surface, you can extrapolate membrane resistance from this kind of experiment. Very nice, simple, everything is automatic. You put your computer and these nice plots come out, if you are good, come out by themselves. But what is important here, that big difference with the direct measurements, traditional one, because you can, in ion conductivity measure in this way, you can change in the frequency, you can follow what happens in the system with time, as function of time. And first of all, you can extrapolate, you can make an analogy of your system with electrical circuit, and where you can subdivide the overall resistance in terms of the membrane solution resistance, the electrical double layer resistance, diffusion by the boundary layer resistance, which is impossible to do with traditional system, which means that in principle, also for traditional experiments, you have a little bit more information between what we call intrinsic membrane resistance, this term here, just related to the, without any boundary layers. That's very important in many cases, because it's related to the flow dynamics. But what is more interesting here, that if this is true and it works, you can use this kind of measurement to follow what happened with time at, not just in the intrinsic resistance, but at the interface, double layer and diffusion double layer, which means fouling. Because if something is changing in this value here with time, is evidence that something is happening at the boundary layer system. It does not happen in this, just in the membrane itself, or just in the solution. Solution is all the same. Membrane is all the same. What is happening, except here you can have some change if you are just eventually fouling by interaction. In this case, you can have also change here, because you block some of the charge, so you decrease ion conductivity in the membrane itself. Forget this term, because that is easy to understand. What's important, you can follow the growing, expanding of boundary layer and of diffusion boundary layers. And so you can predict how fouling, when fouling is appearing, and how fouling is growing with time. That was not done until a few years ago. Today, this is an interesting area of research. And that can be applied not only in ion exchange membranes. For example, we are trying to apply the same concept, the same kind of experiments, also in reverse osmosis. In a system where you can, if really something is happening in the boundary layer, etc., and you can measure by impedance spectroscopy, you can have an idea how the system is changing with time. Quite interesting, and that is a fact on you can find today in literature something, and you will find more and more. Sorry, and that the system is always the same, nothing really changed. You need the reference electrodes, and you have your instrument, you have your solution, and what is important that you can just, through this kind of equivalence, which can be also more complicated, you can follow what happened in double layer, not only what happened in the membrane, but what happened here and here, and that is totally impossible with any other kind of system. So you can extrapolate and understand for everything. Just to close, remember that there are many other ion exchange material that are interested today, and you are living with them. In any fuel, in any system you have, there is a battery inside, and battery are based on the same Nernst equation that we are showing before. And next time we will speak about fuel cell. Fuel cell is nothing more than what you have in front. One difference, that what you have in front, when the battery that's present in this, system you have in front is over, when the chemical reaction between anode and cathode has arrived to the end, you take your battery, you put in the garbage. Eventually, if you're good enough, and the battery is the second kind, not first kind, you take your battery and you put in the, you invert the polarity and you recharge, you re-establish the same system and you start again. This is battery number 2. Fuel cell is battery number 3, in which the difference is that you don't have system arriving to the equilibrium. You supply continuously from the external world hydrogen and oxygen to your system, and you make fuel cell, but the story would be the same. This is an example, very popular today, of battery of the second kind, lithium battery, which is the same that normally you have. Lithium 1 is interesting because this is a battery that has the highest power density in principle available, and is very easy to recharge if necessary. So this one is the second kind. You recharge many, many times, having high power density and rechargeable and light. The other one is a lead battery, the one you have in the car, in the automobile, very heavy. When you take out, it's very difficult to take out. But the chemistry will be the same, and we will see again. What is important here, just to mention, that today, if you want to overcome and to solve the problem of the lithium battery, a lot of people in this department are working on and all around the world to avoid burning, explosion sometime, etc. The real problem is this one. And you have to realize, as we realize in other systems, a system in which you have something happening in the anodic compartment, something happening in the cathodic compartment, oxidation, reduction, etc. But you have to have something that will connect, close your electrical circuit in this solution. And you don't want to mix anodic and cathodic, otherwise there will be, in this case, big explosion. But you want to have a selective system that will transfer in fuel cell normally proton, hydrogen ions. In lithium battery, lithium ions. So you have to, today we don't have this. We don't have a very efficient lithium conducting electrolytes or membranes, solid electrolytes that are what we call membranes. And normally you are using some mixture of ethylene carbonate, dimethyl carbonate embedded in some lithium compounds, etc., etc. But if anybody here is inventing a membranes very selective only to lithium ions, and as we invented and we have for hydrogen ions, so they can exist, big progress will be done here. And today we don't have these membranes available. And, but the one we have are still quite interesting because you can have very high voltage. You can see 4 volts. Remember before we were talking much smaller than this, we had 80 millivolts in some of the battery in the system we were talking before, sodium chloride, etc. Much more. This is 4 volts with a specific energy of a quite interesting value. So if you realize this will be interesting, and you will solve a lot of the problems which today exist. Okay. So just this is one of the, we saw 2 interesting utilization of ion exchange membranes. We saw the electrodialysis and we saw the reverse electrodialysis to produce eventually energy. With lithium battery, we anticipate the most important one for ion exchange membrane, which are all the application in batteries. And we will not discuss too much, except the dimension I made on lithium battery, but we will discuss a little bit more with attention fuel cell, because the fuel cell is this kind of battery. The function is 100% related to the solid electrolyte, which means ion exchange membranes, the one we've been discussing, and that's an area where work can be done. And that will be the prediction I was mentioning to you about this process intensification strategy. The prediction is that in 2050 there will be no more engine by combustion. All the engine will move through electricity based on fuel cell. I don't know if it will be true, but that is the prediction that today people are doing in less than 40 years from now. And that's why fuel cell is one of the areas of interest, and so we will discuss next time about fuel cell. Thank you.